Thanks for the kind introduction. Again, my name is Jianping Pan from University of Victoria in Canada. And this is John Walker with my student Jingwei and my colleague Lin. So I assume everyone has heard about the Starlink, but you may or may not have explored the Starlink yourself. So here is a Starlink, let's say kind of in a nutshell. So I'm using, let's say kind of outgoing packet journey as example here to see kind of how your packet goes from your home to the internet. So when you subscribe to Starlink, so this is what you receive from Starlink. So you have a router and you have an antenna you put on the roof or outside. So by default, the router is at this particular address. So that's why you use a device will be in this particular subnet. So most people just use Wi-Fi to access Starlink. But for us, we do measurement. So we also acquire the Starlink Ethernet adapter and also use this a mini PC as a dedicated device for performance evaluation. For example, this mini PC has two Ethernet ports. So one is for Ethernet, one for the Starlink, and the other one for the regular internet, so we can have remote access as well. So this user router, short for UTR, which is provided by Starlink, but it also can be replaced by user's own router. And in fact, it can be also bypassed as well. But here, I'm just using the default setup. So that's why this router's LAN address will be this. And on the, let's say, satellite side, it has a private, let's say, address. And this will be unique per user dish. So this user dish is transparent to end-to-end traffic, but it's also reachable, let's say, if you try this particular, let's say, IP address. And this is also fixed as well by Starlink. And then the packet comes to the satellite, could be multiple satellites as well if you use inter-satellite link. And eventually everything goes up, had to go down. So that's why we have this landing station here. So they have those specific antenna look like this. And normally the group of 8 or 9, let's say, antennas in particular location. So that's not the end of the story yet, because this device just bring the packet to the ground, but it has to reach the internet access point. For example, in this case is the Seattle Internet Exchange. Then you can go to the internet in this case. So you can see the packet actually goes through a bunch of few things like a dish, satellite, landing ground station, and then coming to the gateway, which is the carrier gradient net gateway here, which I showed for GW. But at the IP layer, this is only one hop. So you can think about we have a space panel here, or you go through inter-satellite links to a remote, let's say, ground station. And then you also have the ground antenna here to bring your packet from the ground station to the CGNAT gateway, and then you get into the POP. So that's why when we do, let's say, network measurement, sorry, the only thing we can measure is from here to here, but we can measure the delay, the latency. So in this case, we can infer whether this goes through the ground station directly as a band pipe, or go to multiple satellites with the inter-satellite laser links as well. So last year, we explored the Starlink backbone. So if you want to see that information, you can find at this location. So starting from this particular slide, then I'm only going to focus on this particular part, which means we do the measurement on the user device, or sometimes we bypass the router, and then go through the satellite ground station, and then come to gateway. So that's the most of the measurement we have done. But in some other measurements we have done, we also deploy a virtual machine near the Starlink POP. So we particularly choose those location which is very close to the Starlink POP. So that's why latency between the virtual machine to the POP will be normally 1 or 2 milliseconds in that range. So in this case, we can also do one-way delay, loss, and throughput measurement. So this gives us the capability if those device, the user device and the virtual machine are time synchronized as well. So this is the setup for our measurement. So now I'm going to show you some measurement results. So for the measurement methodology, and we do have much more details in the paper. So I would highly encourage you to take a look at our paper as well. So if you have questions, you can ask later. So this is the performance we can observe from different dishes around the world. For example, we have a dish on the roof of our computer science building in Victoria. So in this case, like kind of we have an Ethernet access to the dish, and then like kind of we have the kind of dish on the roof. There's no obstruction. So that's why kind of this particular kind of access is the ping sequence. And roughly like speaking, the ping is like in a 15 millisecond interval. And this is the kind of ping, the round trip time, the RTT. And then like kind of we see those, let's say kind of dots here. They basically kind of, those are each like kind of ping examples. And then like kind of we have this clause on the x-axis here. Those are the loss events, which means like kind of we send it, let's say ping packet, but we don't get the kind of response. So we assume like the packet is lost. So in this case, like kind of, although we have no obstruction, we have no, let's say kind of other Wi-Fi, let's say kind of interference, we still see some packet loss. So this most likely would be due to like kind of transmission error happen like between the dish and to the satellite. So in another like location for here, let's say kind of is hosted by our alumni student and in Louisville, like in Colorado. And this one, they're going to use the kind of POP in, let's say, kind of Denver. At that time, when this particular picture is captured, the device accessed the Starlink through Wi-Fi. And you can see like kind of in this case, although like there's no obstruction as well, we can see like kind of the latency jumps up much wider. So by the way, like kind of the y-axis here, all these figures, they're different. We just want to like kind of see each behavior individually. So that's why kind of sometimes like kind of user have better internet performance. It's not because their access network, but their home network because they have Wi-Fi, let's say kind of in their home. So the Wi-Fi like kind of has introduced a lot of like a delay variation in this case. And we also have scenario for them, like kind of this one like kind of in Mississippi and this one like kind of in Ottawa, Ontario, because like kind of we put the kind of dish, let's say kind of in the backyard, not on the roof. So that's why kind of we also have some obstruction here as well. So here, let's say kind of this is the field of view of the dish over time. And then like kind of this red portion here at the corner of the roof, same thing here. So that's why kind of when you have, let's say kind of obstruction, we can see like kind of we have packed loss in a more cluster manner because like kind of once the satellite that you are talking to get behind the kind of obstruction here, then like of course they're gonna suffer much higher, let's say kind of packet loss. So you can see like kind of even for the same, let's say kind of device, let's say kind of Starlink dish, look at this, even with the same, for example, like kind of the sky view, depending like your local access technology, whether you use Wi-Fi or Ethernet, your behavior could be different. So that's why kind of when we do like kind of a measurement, we try to use Ethernet as much as possible. And also like kind of we want to mount the dish on the roof as much as possible as well. So not only like kind of in US and in Canada, we also like kind of have access to dishes around the world through collaboration and interaction. For example, like this dish is in Europe, and this is in Australia, and this is in South America, and this is in the middle of the Indian Ocean, the west part of it. So you also notice like something very obvious here. Is for example, like this shows the minimal, let's say, kind of a round trip time for this short duration. So roughly we can translate the ping sequence into like the ping, let's say, kind of gap here. And this is a very interesting behavior. So that's why kind of we zoom into this kind of ping, let's say kind of sequence here. You can see like kind of here, our minimal like kind of round trip time goes from this much down to here, and then later it jumps up again. So this actually kind of reflect the Starlink satellite and the ground station handover. We mentioned like before, you have a space antenna and you have a ground antenna. Then like when you do ping, your like a single hop in IP layer actually kind of go through both antennas as well. So when you switch to another satellite, chances are that this satellite might be talking to a ground station pretty far away. But once you get to the ground, you cannot get into the internet right away because you have to go to your home pop to get this address like translated to your public IP address. Then you can go to internet. So that's why, especially kind of you have a satellite in the space and then you land very far away from your home pop, then you are going to introduce pretty high, let's say, latency to go back to your, let's say, kind of home pop and then come back. So this is like one of the distinct behavior of Starlink. The second behavior we can see here is like kind of, we can see there's a certain concentration of the ping time during this particular kind of handover interperiod, the period here. So this is because of media access control, because like within the kind of Starlink beam, it's shared by multiple users. And the Starlink kind of use grant and randomize and a kind of mechanism to group, let's say, a bunch of users in the same, let's say, kind of frame. So in this case, like depending like which slot you can assign, you can see like kind of the delay could show this concentration as well. So that's why there's many interesting observations you can see from the kind of Starlink measurement. And we can also see the kind of impact on user population. For example, like this diagram from like the user in Perth and talk to the kind of birth pop as well. Because in Western Australia, like kind of there are very few users, like or very few user densities with regard to the available satellite and also the ground station. You can see like kind of in this case, although you see the spread of the dots, but this scale is only from 0 to 100 milliseconds. In fact, this one has the lowest the kind of round trip time and also lowest like round trip variation as well, because there's very few users there. And so here, for example, like kind of in Sao Paulo here, because this dish is somehow in the middle of the wood. So that's why kind of we have those cluster packet loss due to obstruction as well. And one more interesting thing here is the dish in Seychelles. Like this is an island, like kind of in the west, let's say kind of portion of the Indian Ocean here, because this one like kind of in the south hemisphere, also very close to the equator here, we can see like kind of the dish actually kind of avoid a certain portion of the sky, because this portion is reserved for geostationary satellite. The Space X Starlink and other like kind of LEO satellites, most likely they are reused same frequency people have been using talking with the geostationary satellite. So that's why kind of this portion has to be like kind of avoided when the satellite goes in this region. So that's why kind of you have to switch to another, let's say, satellite in that sense. So this is the behavior we observed in May last year. So you can see like kind of during that time, because the location is more than 5,000 kilometers away from any ground station. So that's why it has to use intersatellite like links. But at that time, the intersatellite link is not very mature yet. There's not many satellites either. So that's why kind of we can see like during handover, we have a huge amount of like kind of packet loss. And also delay goes very high because like the packet get buffered in the kind of link layer when the physical layer is gone. And when the physical is reestablished, now like kind of you see the packet going out. So that's why you have the delay drops like kind of to a reasonable like range as well. But only like 3 months later in August, you can see like kind of now the maximum delay has dropped from 900 milliseconds to like 400 milliseconds. And the loss behavior is much less than the kind of thing we have seen 3 months ago. And of course, we still see the handoff behavior as we see before as well. So you can see like kind of intersatellite link has been greatly improved in these 3 months. So those are the like things we observe the dishes around the world. So now we change the viewpoint a little bit. For example, like kind of we go from the kind of sequence to the frequency. The ping time now is in the x-axis, but it's in the large scale. And this is the cumulative distribution in terms of like how the like delay is like spread out. So this part, because this is in the log scale, so that's why this part actually is much wider than the kind of left part. This is the kind of intersatellite link from May to let's say kind of August last year. So we can see the improvement here, but still it's pretty wide like spread in terms of like its latency. The smallest one, as I mentioned, like here, is the one in the Perth because it not only has the minimal, let's say, kind of round trip time overall, but also let's say kind of has the minimal spread as well in terms of the range from 0 to 1%, because this is in the lot scale. So that's why kind of it's actually much smaller here. So that's why kind of we can see even for non-intersatellite link, the minimal delay could be around like a 20 millisecond here, even lower than that, but it has high jitter. The jitter can go, let's say, kind of in this case, 40, 80 millisecond in that range. So this is somehow like kind of very different for the traditional internet when we come to protocol design and let's say kind of performance evaluation for the application as well. So in addition to those like active dishes, by active, I mean like the dish has, let's say, kind of active subscription and the user have to pay for it. We also measure the dish in the inactive mode. When I say inactive, which means like there's no subscription, the user does not have to pay for it, but the dish is powered. Because the dish is powered, Starlink still like push the firm update to the dish periodically. Sometimes like even weekly or even daily as well. So that's why kind of you can think about the satellite link is still active, but of course like kind of most of the internet is blocked. But still, from the user dish, we can kind of reach certain, let's say, kind of the satellite gateway here for IPv4. For IPv4, if you are inactive, they block the kind of ICMP ping, but you can do ARP ping, basically kind of between the link layer and the network layer. But for IPv6, we can still do, let's say, kind of a ping by this particular kind of address, because this is the kind of CG, no CGNAT, because there's no, let's say, kind of net for IPv6, but the satellite gateway for like IPv6. In this case, even inactive, we can like reach it by ping message. And because like for inactive dish, users still may, let's say, want to resume the kind of service. So that's why kind of Starlink allow the user to reach certain internet endpoints. So in this case, for example, like the connect.starlink.com is to allow the user to, let's say, kind of recover their service. So that's why for this particular IP address, we can reach by like a ping and even like a HTTP ping. Basically, it can do the ping, not in the network level, but also like kind of in the application level as well. So by doing this, we can see like kind of they increase our capability dramatically because now we can not only measure like active dishes, but we can also do like inactive dishes as well. But of course, there's some limitation on what kind of active measurement we can do on inactive dish. So here is a comparison between like an active dish in Seattle and active dish in Victoria, and also inactive dish like in Victoria. You can see normally speaking, kind of inactive dish has low priority because the prioritization is done by the gateway. So the gateway knows this dish is inactive. So that's why kind of its packet will be like kind of delayed when there's condition as well. So this figure shows like kind of when we have two dishes side by side. So this one is like active one, this one is inactive ones, and then we see the kind of satellite they're talking to because they're in the same cell. So they're actually talking to the same satellite, even one is inactive. But then like the user control is happening at the kind of gateway side. So once like enough we have the picture about the kind of access performance, then we want to dive into it to see like what's the difference between uplink and downlink from the user point of view. So when I say uplink, which means like from the user to the satellite and to the ground station, and the downlink is from the other direction as well. So here I pick up one example from Victoria to Seattle. So we can do ping by, let's say, kind of do ping to the gateway to get measured round trip time. But we can also like kind of deploy a virtual machine very close to the Seattle POP, Seattle POP. So in this case, like we also time synchronize the kind of virtual machine, like kind of between these two devices. We can do one-way delay measurement with the ITT. And what do we find? Like for example, this is the round trip, and this is the one-way delay. So roughly speaking, kind of round trip time is a summation of the kind of uplink and the downlink for the most cases. And also we notice like when the round trip goes up, both the uplink and the downlink latency goes up. So which means like kind of they actually kind of use the same tenor. The tenor is bidirectional for the same, let's say, kind of satellite and the same ground station for both like directions. But of course, the bandwidth allocation, they're asymmetric because like kind of naturally, Starlink assign like more bandwidth to the downlink because most of the content go from internet to the user than the user to the internet. So that's why kind of we can see the uplink, there's a contention there. And there's also like a fewer bandwidth as assigned. And for the downlink, there's like more bandwidth, more allocation based. So that's why the downlink behavior actually kind of is better than the kind of uplink. So we can also do, let's say, kind of a transfer layer and application layer, like a performance evaluation. So in this case, like with iPerf, do the TCP throughput for a single TCP flow. So many of the speed tests that you see on the internet, they actually have multiple connections. But here, we're just like going to pick, let's say, kind of one of the TCP connection to see their performance. So this is for the uplink. You can see like the instantaneous TCP throughput is very like kind of spiky here because like the link, let's say, kind of goes up and down. And also like kind of there's an interruption between them as well. But this particular curve, you may or may not be able to see it, but I'll highlight it, is the kind of cumulative TCP throughput. You can see like it's about like 10 to 20 like a megabit per second in terms of kind of throughput for one single TCP connection, which is much lower than people experience with multiple TCP connections. And this is for the downlink. Downlink, of course, like the throughput is higher, like instantaneous like throughput can go above 200 megabit per second data rate, but this may only be able to sustain because you have this particular handover behavior every, let's say, 50 seconds at a fixed interval here. So when you have like enough handover behavior here, if your minimal delay goes up dramatically, then you're going to have timeout. And if the delay drops down quickly, then you have, let's say, kind of the packet reordering. If you have packet reordering, a lot of them, they also trigger like a TCP congestion control, like the transmission as well. So this is gonna bring the kind of TCP throughput actually kind of only about 50 megabits per second overall in this case. So there's some new development for Starlink. So in addition to the user dish, later last year and early this year, Starlink also like deployed the community gateway in Alaska here in Dutch Harbor. So in this case, you can think about a user has a distribution network themselves, local network. And then you have this, let's say, kind of community gateway look like this. This is essentially a mini ground station. And they also use the car band instead of the cool band in this case. The Starlink claim like they can support like a 10 gigabit per second data rate in both directions symmetrically. Of course, it's also very expensive as well. So this is like how much it's going to cost at the beginning, also for each month, for each gigabit per second data rate. For this case, we deploy something called outside like a measurement. Means like kind of we deploy the virtual machine, let's say kind of outside the Starlink network, but we try to like kind of measure the performance over the Starlink to reach certain like kind of user behind the Starlink as well. So in this case, for example, like kind of we go from Victoria to Seattle and then from Seattle to Dutch Harbor. So in this case, like kind of we have two segments of this space, let's say kind of links. One is like from Victoria to Seattle. The other one's from Seattle to, let's say, kind of Dutch Harbor. And because we can also like have the virtual machine there, so that's why we can decompose this into two parts. So for example, this is only from Victoria to Seattle, just like kind of the regular Starlink hop. The second one is from virtual machine in Seattle, very close to the Starlink pop to Dutch Harbor. So in this case, like we only go over the kind of this car band instead of like a cool and car band. So you can see like kind of because the aggregation and also they use much powerful, let's say, antenna here, the communicator performance is much stable, although they still do handover as well, you can say, and also have packet loss. But most of the time, like kind of the latency is much more slow because less user contention, we have user aggregation already. And we do this like kind of with Akamai, and we all do this with Google. The Google virtual machine is in Oregon, but between Oregon and like Seattle, the delay, the fiber optical delay is very stable and very low in this case. So in this case, we can see like the communicator is also a viable approach to satellite communication. So in this case, like we can support many more users with much, let's say, kind of better performance, and of course, at much higher cost in this case. So this happens like could be like in a cruise ship, or maybe like kind of in some, let's say, kind of space vehicles as well. So last but not least, there's a quick comparison between like a Starlink and a OneWeb, because these are the two only, let's say, operational commercial service provider out there. One for consumer service, the other one like for enterprise service. And they have different, let's say, kind of constellation. For Starlink, most like inclined at 550 kilometers around Earth. The OneWeb, let's say, kind of orbit is much higher. It's almost double the kind of distance to the ground surface. But they use the same like kind of frequency band, roughly in the same range. By now, Starlink has more than 6,000 satellites active running there doing service, but like the OneWeb only has 1/10 of it. It's only about 600 of them. And most importantly, Starlink has much more sophisticated ground infrastructure already, more than like 200 ground stations already. But for like OneWeb, it's only about 10. So this is the performance behavior between like a Starlink, so in the green, let's say kind of cross, versus like kind of the OneWeb behavior, let's say kind of in the this like kind of the plus line here. They both go to like kind of Google's like kind of DNS server. So we can see like most of the time, because Starlink like is at a lower orbit, and also you have a much better ground infrastructure, you can land to the ground station earlier to the pop. So that's why the delay is much lower than the OneWeb. But the Starlink, again, like due to the kind of beam spotting, they jump the beam very frequently. From time to time, we see this like a delay spike, and sometimes they even higher than OneWeb as well. So I'm going to give you some more like recent result later as well. So you can see like kind of because the architecture design, the behavior of the Starlink is actually quite different from the OneWeb. From protocol point of view, this has like both pros and cons. And hopefully kind of we can see like kind of another design from Kuiper and from Lightspeed as well. So before I finish, I want to like highlight the two things. One is like kind of we have been observing like Starlink and also OneWeb for let's say more than a year already, and we have collected a lot of data, and we have been like release the data monthly at this particular location. My student like Jianping and manage this as well, and by now we have more than let's say kind of almost like kind of 1 terabyte of data compressed like kind of photon trace result there. And we have almost all these dishes here at different location with different like obstruction and different like kind of orientation in this case. I highly encourage you to take a look at this particular location. You can pull the data and to use the data to drive your like simulation or emulation you have been doing for research as well. Another thing I want to highlight is like actually kind of this is the Leo Kong, let's say kind of seminar, and also like the people at the SRI and Microsoft Research India, they have been leading this like a Leo scope test bed, which are also part of it as well. We contributed notes and also kind of the software update and feedback. And this allow us to have a planet lab over the kind of space, which means like kind of we can have test bed around the world, and we can observe the kind of the certain network behavior as well. So I also highly encourage you to go to this website to take a look at the kind of test bed available to the public by now. So this is my last slide. I'm going to summarize like kind of what we have seen. Like we can see, let's say kind of the Starlink behavior is very interesting. So here I'm showing you a quick video to show like this is inactive dish, and this is like a dish like obstructed. We purpose obstructed dish look like this, and here is like how the dish, let's say, kind of talk to the satellite. You can see like most of the time these three dishes, because they're in the same like cell, so they're talking to the same, let's say, kind of set at the same time. But sometimes they jump to another one because for each cell there are two beams available. One is the prime beam, the other one secondary beam. And so that's why kind of we can capture the kind of behavior of the satellite with regard to the dish, and then we can correlate it with the performance simulation as well. So one like a thing people have been talking about is kind of because you go to the space, you go direct like the path, and the speed of the light is faster in the space than the kind of fiber optical. Sometimes like kind of you can reach like a lower latency over the space than the ground. So this is the case, for example, like this one is the fiber optical from Alaska to Seattle. And this is like kind of the Starlink. You can see for some time, Starlink latency actually is lower than the kind of the fiber optic here. And but sometimes, of course, it's much higher because like kind of we happen to talk to a satellite, let's say talking to ground station very far away. So in this case, you have antenna back to Seattle. So this can cause like some problem. Meanwhile, for let's say kind of the OneWeb is in, let's say kind of this green dots here, they are higher in terms of like latency, but they're also more stable as well. And of course, Starlink has made improvement themselves as well. So at the beginning of this year, they make some adjustment to that like scheduling algorithm. You can see the overall latency kind of goes down. This is 99% high, but they're still above their target. The target is like they want to average below like 20 milliseconds. They're still working on that. One way to do that, they basically add more ground infrastructure. So in this case, like this year, they added 6 more POPs, let's say, in addition to the previous 7. So now like they in total have like 13 POPs in US, which means like the user can reach internet content in a much faster way in NOL. So yeah, these are the slides I prepared. So I'm going to like entertain some questions as well.